speaker is Katie Kinnaird from Smith College, and she is going to talk about comparing songs without listening, from music to TDA and back again. Katie.
So thank you all for being here. I'm going to start my talk with an acknowledgement that we are here in Tampa. Dr. Drew Lewis posted this tweet at the beginning of the summer asking those of us attending MathFest to think about what we might consider saying in our talk. And so I'm not going to try to answer all three of these questions he posed, but I will just say that if you are on Math Blackboard X, formerly known as Twitter, I would recommend following him, among many others. So I want to speak mostly to the people whose reactions to the comments about MathFest being in Tampa as, couldn't you just? It's just 1 week. So I think of this as sort of the justers. Couldn't you just? It's just 1 week. It's just. So I want to talk about my two distinct reactions to MathFest, to being invited to this session. And I will say I had no idea I was speaking in a room this large. I'm very grateful it's very empty. So my first reaction was like, wow, that's really cool to be invited. Jason and I met approximately 6 minutes ago. I did not know him when he invited me, nor did I know the person who recommended me to him. So it was really cool. At Tampa in August, that sounds hot and miserable, and I do not like being hot or miserable. And then, am I really enough of a mathematician anymore to speak? I was a Project Next dot a long time ago. My training is in math, but I have defected to data science and computer science. So a little bit of imposter syndrome. Am I enough? And then I'll get to see my favorite math people, because all my favorite math people go to MathFest. So this reaction had everything to do with my personal and professional comfort. So, being hot, less ideal for me, great for lizards. And my professional comfort, like, am I enough of a mathematician? My second reaction happened a few months later. This is the part where I really am grateful that the room is quite empty, because I'm not used to crossing the personal-professional boundary, which is that a few months later, after I accepted, I found out I was pregnant, which is very exciting. Except Tampa is in Florida, and Florida is very hostile to marginalized people and has made several attempts to limit reproductive health care despite guarantees that are in the Florida state constitution. Some is the sort of maternal care given here. And so, I'm now thinking about health and safety in a very different way than I was a few months ago, because being hot, I can just that for a week. Physical health and safety, that's a very different thing. I do want to acknowledge that I'm very privileged to have these reactions. I am a cisgendered white woman from a wealthy institution that can pay for me to fly in and fly out very quickly. But I hold these two reactions up because I think that they tell a very distinct story of a difference between when I can just and when I can't. I also want to call out my own reaction of I get to see all my favorite math people, because I do. Except a lot of my favorite math people aren't here. And centering on that I get to see them is all about me, and it's not about them. And some of the commentary has been, what is the math community missing by having people not here? And there are consequences, but I just want to take a second to acknowledge the consequences for the people respecting their safety over being here are missing being here. And so what are they missing? They're missing networking opportunities. They're missing sharing their ideas and chances like I have to stand on a stage and add this to my CV, or like a tenure dossier that's going in this fall. They're missing opportunities to hear your ideas and bring them back to their schools and bring them back to their classrooms. So the pandemic also taught us all that isolation is really hard. And the choice of this location is pushing many in our community to continue their isolation. So I wanted to just take those moments to flip the script, because it's not just 1 week. For many of my friends in the math community, this is their conference. This is the one they go to. This is the one that they save all their professional development dollars to be at. So it isn't just 1 week. And I hope that we can think about what we can do to support and advocate for those who aren't there. So I do recognize I just took a third of my talk, but okay. Okay. So now the reason why I was asked to be here. So I am somebody nobody knows what to do with. I exist in 3 fields, mathematics, machine learning, and music information retrieval. I am that orangey triangle in the middle. There's like 5 or 6 of us in the world. And I don't mean this in the geometer sense of like I sat in a room and realized 5 people care about what I do. It's like 5 people intersect in that training. I will also say that mathematics is my most diverse community. But so I sit at this intersection, and it's like, what does that intersection mean? Also, you'll notice data science talk, I am like, I think legally required to have a Venn diagram. Very good. Okay, so what do I mean? I mean that I bring mathematical practices into machine learning approaches for MIR questions and tasks. Okay, so MIR, music information retrieval. What is that? It's a really fun community. It's very small, but it's very fun. You probably use a lot of our tech if anyone uses Spotify, Shazam, Apple Music. Yeah, you're probably using some MIR. So, MIR, I believe, can all be traced to this question: how do we as humans determine if songs are similar? This is a horrible question. Like, this would not pass muster in a mathematics department, because if I were to ask 5 of you or 10 of you how you would make a recommendation to your friend, I'd get at least 12 answers. Some people would be like genre, some would say no, it's emotion, some people would say artist. Other people are thinking about instrumentation, what does it sound like, what does it feel like? And so we can't even agree. Well, okay, the other thing though is that with technologies like Spotify and YouTube, music is dropping all the time. It's no longer the recording industry saying, you are allowed to listen to these 5 albums that we have predetermined are allowed to drop on this Tuesday. And so we have music dropping all the time, and that means we have to have people listening to all of it. And generally when you ask humans to do things, they like to be paid for their efforts to do things like have shelter and buy food and clothing. So what happens if we take humans out of it? So now we're saying, how do we determine if 2 songs are similar if we don't listen to them? Okay, we could rephrase this to sound a little less nonsense, which is, algorithmically, how can we detect if 2 recordings are similar? And I believe that all of music information retrieval can be traced to this question. And so in MIR, we think about tasks. And so I want to introduce you to 4 groups of tasks. So the first one is the music comparison task. There are 2 that I think about. The fingerprint task is, I think, a lot of just same. Same piece of music, same artist, same performance. So your hard drive gets corrupted. Now all of your Taylor Swift songs are just track 1, artist 1, track 1, artist 1, track 1, artist 1. And maybe you're looking for Cruel Summer in particular. So you're matching to that particular recording of it. In comparison, the cover song task is exactly what we think about when we go and do karaoke. We're thinking about the same piece of music, so Cruel Summer by Taylor Swift, but it could be a different artist, right? It could be Dave Kung and BK doing a lovely duet. It could be the same artist, so Taylor Swift, a different performance, deciding to crash MathFest. She's not. Just in case anyone was wondering, that's not happening. Other people doing duets of Taylor Swift, I have no idea. So the structure tasks are another group of tasks that we think about in MIR. We think about the chorus detection tasks, and it sounds like what the name is that we take a pop song and we say, hey, where are all the choruses? Chori. In the segmentation task, we're looking for more than just the chorus. We're looking for large structures. So with pop music, that's going to be your verse, your bridge, your chorus. If we're thinking about classical music, we might be thinking about movements or codas or motifs. So all of these tasks, I think, at some level go back to that question of, are two songs similar? Do they have the same structure? Do they sound the same? So in my work, I try to take structure-based approaches to address the comparison tasks. So I'm trying to look at either cover song detection or fingerprinting, but using something about the structure. So, so far I've told you that MAR has really terribly posed questions that we can't agree what the answer is. We have a whole bunch of different tasks. And then I have more bad news. We don't even really agree what music is, and I don't mean philosophically. I just mean like the objects we study. So we might talk about the signal. So that's the recording or the score. So sorry. We might talk about the feature vectors. So that might be your spectrogram, Mel frequency, Kepler coefficient, what we call the chroma features. So that's the 12 Western tones. Or we might look at this awesome tweed. This is a matrix representation, a self-dissimilarity matrix as popularized by Foote in the early 2000s. And simply, this is a matrix, very familiar with matrices here in math, where the ith j entry is how close is beat I to beat j. So people, when they say I study MIR, they could mean literally any of these, plus about 6 other things. So we have a terribly posed question on an object we can't agree on. Fantastic. So I start with this sort of tweed. This is a mazurka. I know the color is aggressive. Basically, blue, good, everything else, bad. How we read this is from the top to the bottom and then the left to right. So the song starts at the top of the matrix and goes down, and starts at the left of the matrix and goes to the right. So the big blue diagonal that goes from the top left to the bottom right says the song is the same as itself. Good to have a sanity check. Excellent. But that main diagonal isn't particularly interesting to us. It's those off diagonals. So I'm going to just point out the top right. There's a little diagonal that goes from about the first 45 beats to the last 45 beats. And so that's telling us that the first 45 beats of the song are the same as the last 45 beats of the song-ish. In fact, if we look at the top row, we can see that the first 45 beats are similar to about the second 45 beats, and then something else happens, that repetition comes back again, something else happens, the repetition comes back again. Okay, I've stared at this image since about 2010, so like I can do this in my sleep. But this is really hard to look at. There's a lot of colors to pay attention to. It's quite messy. So in my PhD thesis, we built this object where we can see the repetitions a little bit more clearly. And so in this image, my song goes from the left to the right, and the y-axis is just labeling repetitions that occur. And so each row is one kind of repetition, and the blocks are just showing you where those repetitions occur for the beats. And so now it's a lot easier to see that we have 5 things that repeat, and in fact, we can see that those 5 things fall apart into sort of like I would call like a left repeat and a right repeat. So we can start to see some structural decompositions happening. Okay, so when I was a postdoc, I did the thing that you do, which is you go to all the other postdocs' talk, because you're like a little pack. And so you go and you do that. And I'd recommend if you're graduate student, postdoc, whatever, just like go to your friends' talks, even if they're like in geometric number theory that you don't understand. You just go. That's the thing. And so I was sitting there, and my friend kept putting up these barcodes and talking about topological data analysis and all these beautiful matrix and all this stuff. And I was like, wow, they've already figured out how to compare a whole bunch of intervals to each other? Oops, I have a whole bunch of intervals. To be clear, and I do feel I have to say this because I was trained as a mathematician, the left image has topology, the right image does not. We're just going in as a surgical strike and borrowing the metric from topological data analysis. So with my students at ICERM a few years ago, we started to build objects that were inspired by topological data analysis. So the image on the right is the start length diagram. It's similar to a birth life diagram in topological data analysis. And what this does is that each of our blocks are now mapped to a dot on the right side, where the x-axis for the dot is what beat does it start at, and the y is, or the y value is how wide the block is. So all of those top really small blocks, they end up crashing to the bottom of this image. And all of my big blocks at the bottom end up going up to the top of the right image. We do lose that nice, like, okay, we can see how bigger blocks fall apart into smaller blocks that we have nicely on the left-hand side. But on the right side, we start to see a little bit nicer that some of our blocks are like all essentially the same, and that there's some air gapping. And so that was a really nice feature. But what's more is that the aligned hierarchies that I built for my PhD thesis had a really rigid comparison. It had a natural metric in the definition of mathematical natural, but for everybody else is not at all the definition of natural. But it was really rigid. You could only compare things that were essentially the same size. So this left-hand score has about 200 beats, and the right-hand score has about 300. And the aligned hierarchies had no reasonable way to compare them. And we can see maybe there's some things we want to compare here. The left one sort of has 3 towers. The right one has 5 towers. You know, how close are those towers? Are there meaningful comparisons there? What do we see? What do we not see? And so it'd be really nice if we could compare these in some nice way. So what we noticed is we built what we called the start normalized length diagrams. And instead of having that x value for our dots being the beat number, we changed it to being how far through the song you are. So if your song is 300 beats, and your repetition starts at beat 200, we don't place you at 200 on the x-axis, we place you at 2/3. And so what this allowed us to do is compare 2 songs that were drastically different sizes without actually hurting the length of those tiny repeats in the middle. How most people were doing this in the literature before is they would start with that tweed pattern I show you, and they say, let's just shrink everything down to 100, that's fine. But what you could end up doing is end up comparing something that in the original song was 50 beats to something that in another song was 25 beats, because when you shrank them down, you were applying different transformations. So this was pretty exciting. And then we also noticed that we could say things like live from Tampa, it's SNL, which is not a joke that plays very well. But that was fun. The other thing is that there was a very nice comparison that we also borrowed from topological data analysis that overcomes the number of differences in repeated structures in each one. And critically, it observes the triangle inequality, which I know, as mathematicians, you're like, duh, of course all metrics observe the triangle inequality. This thing that was very important to me. Anyways, so what are some results? I did the aligned hierarchies, as I said in my PhD thesis. We worked on the fingerprint task, so that's that same task. And we did great. And in data science, if you find an error in the data key, like that is like super gold star. We found an error in the data key. It was really great. And then I had also built another object called ASH, the aligned subhierarchies, to work on the cover song task. My students, SNL and MAP, so we made another extension also in topological data analysis, did better than what I had done in my PhD thesis for ASH. And I will also say that their initial results came out in about 10 days. Maybe it was 14 when we wrote it up. Then 2 were undergrads and 1 was grad student. So that was pretty cool. So if you're interested in some of this work or playing with specifically the aligned hierarchies, a group of my students at Smith have just released a Python package. I was raised as a mathematician, which means all of my code was originally in MATLAB, which is a highly proprietary language. We have now released it all in Python. And the paper and the code was part of a submission to the Journal of Open Source Software, or JOSH. Some of you might be more familiar with JOSH's sibling, Jose, the Journal of Open Source Education. We also have code that you can read. And thanks for listening. So do you mean when you say, sorry, when you mean identify a song, you mean like the Shazam style, like hold up my phone and like, what is this? Or do you mean, okay, so I don't work at Shazam. I feel like I always have to say these things. So Shazam's, the older version of Shazam, pre-deep learning models, my understanding was it was a dictionary learning kind of lookup system. And so if you use Shazam when it first came out, you'd hold up your phone, and if it was a pop song, it got it right away because it was easy inside the dictionary, versus like if you went to a coffee shop where they play like all new age, it was like, we don't know, this is not music. Now it's a lot better, and I think they've spent a lot of time thinking about query by humming, because now it works on humming a lot better. I believe they're using deep learning though. Music information retrieval, like everything, has been taken over by deep learning. And to the question about ChatGPT for music, there is one, and I couldn't look it up fast enough what the name of the system was. It just came out like 6 weeks ago. The cover song detection task, similarly, there are some deep learning approaches. It also boils down to how diverse your data set is. So kind of one of the toy data sets, so Mazurka's is like toy data set 1. You could kind of think of that as like your like infant data set, and then your toddler data set is the Beatles data set. It's actually quite hard to do the cover song task when you just have one style or one type, because it can kind of overfit. But on the other extreme, you don't want to have like millions of songs, because then it also does quite poorly. So the unsatisfying answer that I'll give you is like, it depends on what your data is. It depends how good you want it to be, and it depends what your emotional feelings about deep learning are. So someone raised as a mathematician, I am deeply suspicious of deep learning. I'm more fine with it for generating music. I'm less fine with it for making decisions. But that's a much longer conversation.
Thank you.
I think, yeah.
I wanted to ask if any of those data analysis techniques have been used in a legal setting, like when one artist sues another for copyright?
So there is a version of the fingerprint task that we call the authentication task. I do not work in it. I don't actually know anybody in MIR who academic conferences who works in music authentication. It's not a particularly interesting task from a research perspective. That being said, there's a really famous example actually in the academic literature of the Hato recordings. So if I remember the story correctly, there was a sort of reclusive pianist who would kind of disappear for periods of time and then release an album. And so there was an album released under this person's name, but it turned out that like it was really spliced recordings of other people. And so that particular case study has been studied a fair amount in MIR. Michael Casey, Malcolm Slaney, and Christoph Rhodes, I believe, have a paper on that. But the Hato recordings, it's sort of this famous, like this album came out, and like how people do that legal for authentication is not something I have ever been involved with, and personally would want to stay extremely far away from, because it really isn't, really that interesting of a task. Like, it's kind of the equivalent of like when you tell people you have a PhD in math and they're like, oh, so you're like really good at like computing the tip? Like, yes. Or like you do really hard calculus. Like it just kind of feels like it's not a particularly interesting question. So yeah, I don't know how any of that legal stuff happens. Yeah, I've also never worked in industry, so I don't know all of the behind the scenes for some of them. I've had friends, obviously, at all the big ones, but yeah. Oh, sorry. Yeah, go ahead. Yeah, so I'm just going to repeat the question back. Like, does the changing of the section lengths make it more difficult to figure out cover song detection? And so I'm going to give another really unsatisfying answer, because that's pretty much all I do, which is it depends how you pull your features. So one thing that seems really easy to do as humans is to pull beat synchronous features. So if you ever, like, you listen to a piece of music and you hear yourself kind of padding along, you're finding the beat. And even if I'll often meet people that are like, oh, I'm terrible at that, computers are way worse. So pulling beat synchronous features can sometimes help with that. But also when you're doing cover song detection, you can do it in a couple different ways. You can either say, I want to look at the whole song and compare it to another one. And I think that would be really hard if somebody's really messing with the length of a section. But a lot of techniques, again, in the pre-deep learning era, were just like, I'm going to take 30 seconds, or I'm going to take 40 beats. And so you're just kind of comparing like little snippets to each other. And then it doesn't really matter if somebody got obsessed with, Hard Day's Night by the Beatles and played the chorus 14 times in their recording, because all you're just grabbing is 30 seconds. So it depends on how you pull your data, which is like data science's like least satisfying answer to every question. So thank you.
Okay, thanks, Katie.